I'm Wil McCarthy, Futuresmith. I'm the author of Rich Man's Sky and other science fiction novels. You can find out more at futuresmith.com. So called hard science fiction is fiction where the science is correct, or at least sounds correct enough to satisfy a demanding audience. In this series, we'll explore how I've used simple calculations in a spreadsheet program to work out technical details for science fiction novels like Rich Man's Sky. Hi, today we're going to talk about transfer orbits. I've got a transfer orbit represented here in a little drawing. Let's say this is the Earth here, and you've got a circular orbit around the Earth. And let's say you want to go somewhere else, like, say, the Moon. Then you want an elliptical orbit that will take you from the Earth to the orbit of the Moon if the Moon is orbiting out here. What we do when we get to the Moon is another transfer orbit. We transfer from this highly elliptical orbit to another circular orbit that's around the Moon. So, how do we do this? There are two equations that matter for this. Orbital mechanics is very complicated, but we can distill it down to a couple of critical essences, namely, how fast are we going and how long does it take? Um, so, how fast are we going is this equation here. This mu is a thing called the gravitational parameter. Uh, it's the mass of a planet times the gravitational constant. The gravitational constant is a universal number, um, but this value mu, you can just look it up in an encyclopedia. You can look it up on Wikipedia. Every planet has its own gravitational parameter, and we'll look in a minute at what that looks like. Anyway, it's the square root of mu times this value here, which is 2 over r. R is your radius at any given time, the radius from where you are to the center of the planet that you're orbiting, um, minus 1 over a. And a is a thing called the semi-major axis. If you look at this ellipse, uh, it's got a diameter, a long axis here, which is called the major axis, and it's got a short diameter here, which is called the minor axis. The semi-major axis is simply the distance from the center to the one of the long ends. So when you have a circular orbit, R and A are equal to each other at all times. When you have an elliptical orbit, R changes constantly, and A is a constant value that's this distance here. Uh, so the orbital period, which is how long does it take you to complete this orbit or this orbit, uh, is 2 pi times the semi-major axis cubed divided by that same gravitational parameter. Now, these are pretty simple equations. They might look a little scary, but we can easily uh, demonstrate them in Microsoft Excel or any other spreadsheet program of your choice. So we've got some useful values programmed in here. We've got the radius of the Earth in kilometers and in meters. We've got the radius of the Moon in kilometers and meters. We've got the radius of geosynchronous orbit, uh, just because that's fun. And we've got the radius of the Moon's orbit, uh, which is 384,400 kilometers. The Moon is pretty far out. Uh, and then the gravitational parameter, this is measured in meters cubed per second squared. And, excuse me, it's obviously a lot larger for the Earth than it is for the Moon. For the Earth, it's 4 times 10 to the 14th. And for the Moon, it's 4.9 times 10 to the 12th meters cubed per second squared. And again, you don't have to be intimidated by this. You can just look these values up. They're not hard to find. So we're starting with, again, this circular orbit around the Earth. And what that looks like is we'll just represent in meters our, we've got two locations that matter, the periapsis and the apoapsis. Um, Periapsis is when you're closest to the thing you're orbiting, and apoapsis is when you're farthest. Um, this is sometimes called perigee and apogee, but those are specific to the Earth. Uh, if you're an astronomer, you'll talk about perihelion and aphelion being the closest and farthest points from the sun, and you get other sort of Greek names depending on what body you're orbiting. So we'll just use periapsis and apoapsis because they're the more generic terms. So we'll assume that we're orbiting right at the center of the Earth. We know that's not true. We know we're actually orbiting, a few hundred miles above the Earth, but for purposes of this calculation, it doesn't matter very much. If we plug in the radius of the Earth for both the periapsis and the apoapsis of the orbit, our semi-major axis is the same as both of those values. That means we're orbiting in a circle. For the gravitational parameter, we'll use the value for Earth, 4 times 10 to the 14th meters cubed per second squared. And then this calculation here, which we take from our velocity equation here, we can very simply calculate our velocity at periapsis and apoapsis. It's the same velocity in both cases, which is 7.9 kilometers per second. So we'll plug that in. We'll just write it down here. We'll make a note. 7.9 kilometers per sec at Earth. And now we have also our orbital period, which we'll express in hours. It takes about an hour and a half to orbit the Earth in low Earth orbit. 1.4 hours is a little bit unnaturally low because we're ignoring the atmosphere. We're pretending that we're orbiting directly at the surface of the Earth. So in reality, it'd be a little over 1.5 hours for any realistic orbit, but that's okay. We're trying to keep this very simple here. All right. Now, if we're going around the Earth in a circular orbit, and then we want to make a transfer orbit to take us to the moon, not take us directly to the moon, but take us to where the moon is going to be by the time we get there. We want to get there at the same time that the moon does. What we want then is to change our apoapsis. We have the same periapsis, but we want to make our apoapsis the distance of the moon's orbit. So again, we're going to do this in meters. We copy this value here, and we paste it right here. That didn't work. Let's paste the value. And again, we'll color that green. I like to color things green if they're input boxes rather than calculated values. The calculated values I leave as white. So now you see something very different. You see that our periapsis and our apoapsis are very different from each other. Our semi-major axis is half of the radius at the apoapsis. As you see here, it's about half. It's this distance here. It's the semi-major axis divided by 2. Now, what we'll see here now is that our velocity is much higher. Our velocity in meters per second is suddenly so large that we really want to know what it is in kilometers per second. So let's take that divided by 1,000. It's 11.1 kilometers per second. So 11.1 kilometers per second at transfer orbit. What this means is we have a delta V, a change in velocity of 11.1 minus 7.9. So we have a delta V of 3.2 kilometers per second. That's a pretty hefty velocity change. Um, Not as much as it takes to get off the Earth. To get off the Earth, you've got to go from 0 to 7.9 kilometers per second. That's why the Apollo rocket is very big on the bottom and small on the top. You need a smaller booster stage to get you from Earth orbit to the moon than you do to get you from the surface of the Earth to the to Earth orbit. Um, okay, but that's how fast we have to go then to get to the moon. I've misspelled transfer. Let's fix that here. These are just our own personal notes that we'll use in perhaps writing a science fiction story or whatever it is we're doing. Um, Now, once we get to the moon, an interesting fact here, uh, this orbital period is 9.9 days. Uh, that's not the time it takes us to get to the moon. That's the time it takes us to complete this entire ellipse. So the time to get to the moon is half of that. So we take this and we'll divide it by 2, and that's about 5 days. So it takes us 5 days to get, whoops, to get from here to here. Now, for those of you who are students of history, you'll notice that the Apollo astronauts got there faster than that. They weren't doing this kind of perfect, ideal Hohmann transfer. They were going faster uh, than what we're modeling here. What we're modeling is called a Hohmann transfer. It's the most energy efficient way to get from one place to another. Uh, so anyway, uh, 4.9 days. We'll make a note of that as well. And then what happens when we get to the moon? Well, now we're going to change planets. So we'll copy this value to here, pasting only the value. And now we will change our orbit to be circular. Around the moon. And now you see that our uh, velocity at periapsis and our velocity at apoapsis are both the same. They're 1.6, 1.7 kilometers per second at the moon. So 1.7 km per sec at, oh, hang on a sec, I skipped a step. Let's undo a couple of things here. It won't let us undo, okay. All right, so we're back at Earth now. Velocity at apoapsis, this is important. 184, so 0.1, 0.2-ish kilometers per second at top of transfer orbit. So this isn't a delta V that we need to make. We just lose this velocity. We're starting out at 11.1 kilometers per second. But by the time we get to the very top of this ellipse, we're practically stopped. And then we speed back up and then we slow down just like that in a nice gentle orbit. So then now let's go back to our lunar orbit. We do that by, once again, we change planets here. We plug in the value for the moon instead of the value for the Earth. Now, once again, our radius, we're going to put in the radius of the moon. We're imagining again that we're orbiting right at the surface of the moon. There's nothing actually to stop you from doing that. There's no atmosphere on the moon. It wouldn't be very safe. You might hit a mountain. So you really want to go a little higher than this, but we're going to model it in the easiest possible way, just using the radius of the moon. Um, Now, let me move this over here so it's not in our way. Now, this tells us that the velocity that we're going at the moon is, when we're orbiting the moon, is about 1.7 kilometers per second at lunar. This is another delta V that we have to put in. So that, well, 1.7 minus 0.2, that's 1.5 kilometers per second. So this is the delta V that we need. This is the change in velocity that we need to circularize our orbit when we get to the moon. And the period of time that it takes to orbit the moon is about 1.8 hours. You'll find, it was about an hour and a half to orbit the Earth. It's about an hour and a half to orbit the moon. It's a curious property of orbital mechanics that no matter how big the object you're orbiting, if it's a rocky planet and you're orbiting close to the surface, it's going to take you about an hour and a half to go around it. That's just a cool side effect uh, of uh, of the orbital mechanics complexity boiling down to something simple. Anyway, if we want to know what our delta V looks like, well, we have 7.9 kilometers per second to get off the surface of the Earth, maybe a little more than that to overcome atmospheric resistance, uh, and then 3.2 kilometers to go from the Earth from Earth orbit to a lunar transfer orbit, and then another 1.5 kilometers per second to get out of our transfer orbit and into an orbit around the moon. So we can draw that here. We'll just copy these. Just like that. So that's where we're circularizing our orbit when we get there. And that's how we model a transfer orbit. Uh, I hope you found this informative. Please like, follow, and share. Thank you. Bye-bye.